Hello everyone. Today we're going to look at the pImpl idiom in C++. And first we're going to do a brief overview of what it is, when to use it, and then we're going to show an example implementation. And what you might think it is proof that programmers don't care what you think about their naming scheme, but it actually stands for pointer to the implementation, and it'll make more sense shortly. CPPReference.com has a pretty good description that we're going to mainly go off of today. Alright, so let's just read the intro together, shall we? Pointer to implementation, or pImpl, is a C++ programming technique that removes implementation details of a class from its object representation by placing them in a separate class, accessed through an opaque pointer. So if that doesn't make sense, that's okay, we'll soon. Here's a quick example. We have a class called a widget. It has a private member, well, a struct that is a forward declaration of the class that is its implementation. They're using struct here, you can do structor class, it's fine. And then they have, don't worry about this, propagate const, we are not going to be using that. It has a unique pointer to that implementation. And then in a CPP class, we define that struct. Now that is it in a nutshell, but there's more to it. One of the great things it does is it reduces your compile time dependencies. And that'll make a little more sense later, but yes, it can speed up compilation if you're changing code. Okay, let's go over this explanation, because this is kind of the crutch of what it does. Because private member data of a class participate in object representation, affecting size and layout, and because private member functions of a class participate in overload resolution, this takes place before the member access checking, any change to those implementation details requires recompilation of all users of the class. Normally, if you have private data members and private stuff in a class, if those change, anything that uses the class has to recompile. However, in this sort of setup, and this is one of the advantages, if the implementation changes, then this CPP object is the only thing that needs to recompile. Anything else that is using your widget does not need to recompile. So it can speed up compilation times if you're just changing the implementation details. All your other objects in your project don't necessarily need to recompile if they're using it, so you can get some faster compile times. That is the main thing, the main advantage, in my opinion. There's a few others which we'll see. pImpl breaks this compilation dependency. Changes to the implementation do not cause recompilation. Consequently, if the library uses pImpl as its ABI is Application Binary Interface, newer versions of the library may change their implementation while remaining ABI compatible with other versions. Alright, let's talk about the ABI for a second so that all makes sense. In computer software, an ABI is an application binary interface. It's an interface between two binary program modules. So it's basically the way two different things talk to each other, is the simplest way to think of it. Alright, let's review the trade-offs. The alternatives to the pImpl idiom are, well, the inline implementation. Private members and public members are members of the same class. Or the pure abstract class, where the user obtains a unique pointer to a lightweight abstract base class. The implementation details are in the derived class that overrides its virtual member function, also known as the OOP factory. Alright, so they call this feature of it being separate a compilation firewall. In simple cases, both pImpl and factory method break compile time dependency between implementation and the users of the class interface. Factory method creates a hidden dependency on the vtable, so reordering, adding, and removing virtual member functions breaks the ABI. We haven't really talked about vtable before. It's a virtual method table, or a virtual function table, a virtual call table, a dispatch table. It's basically what your program's whole front end of callable functions. And generally, these don't contain the definitions. They just contain like a lookup table for everything available. These are, of course, specific to virtual functions. The pImpl approach has no hidden dependencies. However, if the implementation class is a class template specialization, another thing we haven't really talked about, the compilation firewall benefit is lost. The users of the interface must observe the entire template definition in order to instantiate the correct specialization. A common design approach in this case is to refactor the implementation in a way that avoids parameterization. That's a mouthful of a word, isn't it? This is another use case of the C++ core guidelines. Don't over-parameterize. We're not going to get too off topic on the template specialization, but just know that if you've got template specialization going on, you probably don't want to be using this pImpl idiom. Alright, just a few more things here and then we'll get to the coding. We want to talk a little bit about the runtime overhead. There's an access overhead because each call to a private member function indirects through a pointer. So as you define your interface, you're going to have to go through a pointer to access the implementation for basically everything. This is a pretty small overhead, and it is often optimized away. Each access to a public member made by the private member indirects through a pointer. So as we're designing the implementation, you can make a pointer back to the interface, so there is another indirection if you need to access stuff in the interface from the implementation. Both indirections cross translation unit boundaries, and so can only be optimized out by link time optimization. Another thing that might be confusing to newer users, but basically as you compile separate objects and they link together later to make your final program, there is unit boundaries and they cross them using these pointers to each other. So sometimes that'll get optimized away and become faster than you actually programmed it by your compiler. And they do note here that object-oriented factory requires interaction across translation units to access both public data and implementation details and offers even fewer opportunities for the link time optimizer due to the virtual dispatch. Okay, space overhead adds a pointer to the public component, and if a private member needs access to a public member, another pointer is added to the implementation or passed as a parameter to each call to the private member that requires it. This is what I was talking about earlier, where you need a pointer back to the implementation sometimes. Lifetime management overhead. pImpl and OO factory place the implementation object on the heap, and that can impose significant runtime overhead at construction and destruction. They may be partially offset by custom allocators, since allocation size for pImpl is known at compile time. On the other hand, pImpl classes are move-friendly. Refactoring a large class, such as a pImpl, may improve performance of algorithms that manipulate containers holding such objects. Although movable pImpl has additional source of runtime overhead. Any public member function that is permitted on a moved from object and needs access to private implementation incurs a null pointer check. Maintenance overhead. The use of pImpl requires a dedicated translation unit. Header-only libraries cannot use pImpl. Introduces an additional class, a set of forwarding functions, and if allocators are used, exposes the implementation detail of the allocator in the public interface. Since virtual members are part of the interface component of pImpl, mocking a pImpl implies mocking the interface component alone. A testable pImpl is designed to allow full test coverage through the available interface. Kind of important. I'm not sure if we'll get that far in this episode, and let's talk a little bit about this implementation. The object of the interface type controls the lifetime of the object, and the pointer to the implementation is usually a unique pointer, because unique pointer requires a pointed type. Pointed to type is a complete context in any context where a deleter is instantiated. Special member must be user declared and defined outlined in the implementation file. Alright, and they talk about the propagate const. We're not going to worry about that a whole lot. It starts getting experimental, basically, so we are going to keep it a little more simple. You don't really need to worry about that a lot, but it is more advanced. If you want to try to figure it out and understand it, that's fine, but I wouldn't recommend it on the initial understanding of pImpl, just because I think it overcomplicates it. All private data members and all private non-virtual member functions are placed in the implementation class. All public, protected, and virtual members remain in the interface class. If any of the private members needs access to a public or protected member, a reference or a pointer to the interface may be passed to the private member function as a parameter. Alternatively, back reference may be maintained as part of the implementation class. That'll make sense later. Non-default allocators are intended to be supported for the allocation of the implementation object. Any of the usual allocator awareness patterns may be utilized, including allocator template parameters such as standard allocator and constructor argument of standard memory resource. Alright, and now for an example. Our example is going to start out a little like this, and we're going to talk all about it. I made a poll earlier this week and asked if you guys wanted the next C++ tutorial recorded on Windows or Linux, and you guys pretty overwhelmingly voted Linux. So we're going to be using that to program up this pImpl idiom and test it out. I've also been informed that it's pronounced like Canucks. Alright, welcome to my Linux shell, where we are going to use GCC. Let's check the version. We're on 9.3. Very nice. And we're going to make a pImpl implementation. Alright, a nice clear screen here. And the first thing I'm going to do is change directory into my repos. And then I'm going to make a directory called pimp. And let's go ahead and make this a little larger so that you guys can read it clear. And now we just want to make the basic structure of our piece of software. So we're going to make a CMake file. We're going to use the touch command to do that. CMake lists.txt. And we're also going to make our main files. We're going to make our driver file to run our stuff as a main.cpp. And we're going to make a class. And we'll just call it, let me think of something here. Oh, why don't we stick with the whole animal theme? So we'll just call it an animal. So we want to make all those files. And now, I think I've done this wrong. I want to move all these into the pimp folder. Alright, now let's go into the pimp folder, take a look, and it's all there. So we just need to work these up. We're going to use Visual Studio Code because there's no way I'm doing this in Vim. We'll have several crashes guaranteed if we try that. Alright, looking good. Let's see, Visual Studio Code has notified me that CMake list.txt was not found on the root folder. How would you like to proceed? I would like to proceed with you getting good because it is there. It just doesn't understand. So let's just make some basics CMake stuff to get this compiling because, well, we could just run the GCC commands, but why not use CMake? It makes it easier, and it makes it easier to expand later. We could optionally, of course, just use a makefile, but CMake's going to make our makefile and simplify all that. So basically all we're going to need here is a minimum version, and we do have the CMake extension here. It's just CMake tools. I guess we have a couple of different things here, but it is kicking in and helping us remember all these. CMake minimum required version. We're just going to go with 3.1. We could also go CMake -v, dash version then. Okay, 3.16. So we could say 3.16. That's what we're using, but it's not super critical. Let's give this project a name. We're just going to call it pimp. And we're going to add an executable. And we're going to say, hey, this executable is the project name, which is going to be pimp. Now, some projects have multiple executables and libraries and stuff. In that case, you don't want to make your project name the executable. But since we're just doing a single one, that's how we're going to do it. And we're just going to call this tutorial that. Oh, we need to add on all the all the files, which we can just click over here and see. So we're going to have a main.cpp animal.h and animal.cpp, and that should take care of the CMake. Now we just need to program up these files. Let's make a quick int main, and of course we're going to include animal.h because we'll be using that. And in this animal, this is where we're going to make our whole pointer to the implementation deal. So what are we going to need here? We're going to need, well, of course, the class. Well, let's start with the headers. We're going to need memory because of the unique pointer we plan on using. And basically, we're just going to use a class, and we're going to call it animal, and it's going to have public and private members. And the main thing here is we have another class called the implementation. This needs a name. Well, we're going to stick with the very simple name of pImpl, and we might rename later. And basically here we're going to make a unique pointer of it. Standard unique pointer of pImpl. And this unique pointer needs a name, and we'll just call it pImpl. Alright, and that's the core of that, but of course we're going to need some more things like constructors. Now this is where it kind of gets interesting, is with these constructors, because you need several constructors. Well, there's a few kind of core things you need. You need a copy constructor. That's going to be one that you basically have to have publicly available. So we're going to make animal, and we're going to make a const to another animal by reference, and we're just going to call it A. Oh, we don't want to define that here though. We'll define that in the implementation where we have access to this thing. You know, I don't actually think we need the copy constructor. We can even say actually specifically no copying this because, well, it is a unique pointer. We don't want to copy it. Let's spell animal correctly. However, what we do want, I'll leave a little comment here. Delete the copy constructor. I know I spelled that wrong. But let's see, we do want this one. We want animal double reference. And that is going to be our move constructor. Another thing we're going to need here is we're going to need to define a destructor. Now this is actually another required thing. So animal destructor. We'll define that shortly. Now we might also want just a default constructor, and that's fine. You can even have some constructors with parameters. We're not going to worry about that a ton right now though. Some other things that you probably want here are equals operator to do the move. So you can overload that by going, let's see, animal. Let's see, that's what it's going to return. So we're going to return a reference to this animal, and operator, no, not delete, equals, and then the name of the class. That way you can set one equal to another via the move operation, or by constructing a new one. And since we're doing that, we also want to delete the copy version of this, which will be operator equals, and this one is going to be const animal by reference, but we're going to say delete it. Alright, so there we go. Looking pretty good. We're allowed to move, but we're not allowed to copy. Now the base reason for this, if I understand this correctly, is because, well, if you're doing a move operation, you're essentially transferring ownership of this unique pointer, which is fine. You can transfer ownership and essentially give it away, but you can't make additional copies of it because, well, it's unique. That would be something more for like a shared pointer. Now, of course, we want some kind of functions to actually operate on this class, so we're going to put those up here somewhere, and these will use the implementation. So let's make a void. What can animals do? Well, they should all be able to eat, so we'll make an eat function. Sure. And maybe we'll give it like an amount. So like maybe we'll just go with integer for now, and we'll call it calorie. How many calories is it eating? We'll say. And we don't need to make any private stuff for this because that's going to be in this implementation. And we'll make something else. We'll check fullness. So we'll go return an integer on this one, and we'll return, and we'll just call fullness, pass in no parameters, but we're going to need access to this, and we're basically going to return the fullness. So let's go ahead and design these few functions in animal.cpp. So in here, we'll include, of course, animal.h, and we just need to make these functions now. So we're going to copy these signatures, put them over here, put animal in front of them, and give them a definition. But they need some data to pull from, and that's where this implementation comes in, this right here. So we need to define that. And the way it's defined is like so. Well, it's animal, and then it's pImpl, and we need it to be a class or a struct. We're going to go with class here. You can do struct if you want. It probably should be struct. And we just need to give it a definition. Now this is private in the CPP file, so nothing else has access to it except for this animal, which is essentially an interface at this point. So we're going to just make some public members, and we're going to have int fullness. Now this is going to start out with some default constructor, maybe 10. So now, maybe we want this to be get fullness. Sure, let's do that. Let's put a get in front of this, just to make it clear that's what we're doing. So now what this is going to do is it's going to get this implementation, but it's going to get it through this unique pointer here. Also, we need to work up our constructor a little bit and make sure we actually instantiate this correctly. We'll do that in a second. Maybe I should do that first. Then it'll essentially be making a unique pointer of that there. Well, let's just do that real quick. We'll go animal, animal, and we're going to say the pointer to implementation is equal to standard make unique of type pImpl, and pass it nothing. And there we go. That should take care of the definition of a default constructed. Do we have any other constructors that we might use? We might use this one. We'll worry about that one in a second. Let's go one at a time. Okay, so let's work out these functions. So it can eat some calories. Very good. So how does it do that? You gotta fill out this struct basically. And so what we're gonna do here is we're gonna take that implementation and we're gonna say fullness plus equals calories. And now we're adding calories to the fullness. And to get the fullness, it's very similar. You just return that data. But you got to go through this pointer like we talked about earlier. And there we go. Do a little formatting. Looks good. Okay, so maybe we want some checks in here. And naturally, we probably do. So, like, how many calories can you eat? Can you just eat them endlessly? I don't know. Probably not. Well, we probably have a cap. So, let's just give it a hard cap of like 100. And we can do that anywhere we want. We can have a const somewhere in this class that does that. I like the idea of having a static const. There might be a better way to do this. But that way, yeah, it's gonna only make one variable of this no matter how many animals you have. And we'll say max fullness. And we'll just say it's 100. Okay, that should be okay. It might not like being initialized there. But we can say, okay, so if you add the calories to it, very good. Then we'll say if the fullness is greater than max fullness, well, that's not legal. So then we're just going to set it back to that. So if you try to overfill yourself, it's just going to cap out, basically. And if you want to improve this code, it is going to be on GitHub, link below. You're welcome to work on it and make a pull request. All right, that should be good. We need to make these constructors and destructors. So we'll go ahead and do that right about here. And of course, we want to put this in front of them. And now we don't need to really do anything too special here. So we're just going to say equals default. But they do need to be defined. There we go. That should take care of those. So that makes those pretty easy. And let's see what else here. That's a decent starting point. Let's go ahead and do a few just quick examples here in our main. So let's instantiate a new animal, whatever that is, animal, and we will call it a cat, because why not? And we'll say cat dot eat, and we'll give it a 10, and then we'll just say the fullness. And maybe we'll do a before and after. So standard cout cat fullness before eating. And here we would go cat get fullness in line. And then we'll just do the same thing here, except it's after. And now we should have 2 lines, and that should work. So let's go back to our Linux command line here. And let's go cmake. Let's make a build folder, make their build. And then we can cmake capital B for build folder. Tell it to build there. Tell the source, capital -S, is in this current folder. There we go. Looks like it built okay. Now we can change directory into our build and do an ls, and we'll see that there is a make file. Now we want to actually, well, that's configure. I said build, but really it's configure. Now we want to just run this make file to build our software. And it looks like max fullness doesn't have a type. Massive oversight on our part. If you caught that before I did, congrats. But basically we just want this to be an integer. That'll be fine. Alright, back to the Linux command line. And since we didn't change any files, we don't need to rerun cmake. We can just run make again. Looks like it doesn't know what cout is. That's because we didn't include IOStream. So that should take care of that. Let's do another clear and a make. And it looks like we forgot to put a semicolon after a class definition. So that should be right here. Very good. And we can run make one more time. And it's complaining about something. Invalid use of destructor animal as type. Oh, yes, we put that little dashy in the wrong spot on there. It should be over here, because that's how it works. Let's run make again. Still has one more complaint. Names the constructor, not the type. I gotta look at that one. I don't know what the problem is there. Names the constructor, not the type. Yes, okay. So it needs a return type here, and that's the return type. And the scope thing goes here. So just doing that correctly would help. Yeah, I don't know if I need to explain that further. All right, so now let's try it. There we go. We got a successful build, and we should be able to run it. Let's do another ls, and there's our program. So let's just run it with the /pimp. Cat fullness before eating 10, after eating 20. So as you can see, it is working, and it is filling out that implementation and updating that fullness through these functions. Okay, so now let's look at using the move constructor and the move equals operator and see if we can get those to work properly in an example. So let me just show you some failed cases here and some errors you could run into if you're doing this with a move constructor. So say we make another animal, and we'll just call it other cat. And we're going to set other cat equal to the previous one. Yeah, that'll be fine. Let's go ahead and clear this up a little bit. So this is going to try to copy, because that's what this does by default. It's just a copy. So let's see what happens here. And you can see I've already tested it a little bit. It'll say use of deleted function, const animal by reference. And so yeah, it is because we deleted this here, this copy equals operator. And it's going to be essentially the same if we try to construct it from another cat. It will do the same thing. Might give a different wording of the error. But yeah, use of deleted function. And so what we actually have to do is put standard move in front of this. And that should work. That should compile. Now let's go ahead and try to compile that. Clear first. And it compiles. But let's see if it runs. It runs fine. But something very critical happened that is not really shown in this that will cause you problems down the road. When you move this old one, you release control of it, it's essentially gone. So if we try to like see out the old cat again here like this, or use any of its functions, that's the original cat, the data is not going to be there anymore. So calling to this is going to cause a problem. All right, save that. Let's recompile and take a look. Make. Compile's fine, but when we run it, we get a seg fault. The reason it's seg faulting is because when we call this, the implementation is no longer there. This here, what we made unique, has been moved to the other cat, and this one no longer has one. So yeah, you got to watch out for stuff like that, because your compiler isn't going to find that. But we could say other cat, and it's going to have those implementation details. And this will be okay. But the problem here is, well, this previous cat, it's gonna, the implementation's still gonna sit there, or not the implementation, the interface is still gonna sit in memory. So you gotta think about stuff like that. If you're passing this off via a move, then you wanna be sure to deallocate the old one. And the easiest way to do that might be to use something like a pointer instead. Let me just go ahead and run this with the other cat, get fullness, just to show you. It should also keep the fullness. So it should have 20. Yeah, there we go. Maybe I'll say other here. Yeah. All right, so what can we do instead? Since we don't want to accidentally have this one floating around without its implementation anymore since we moved it. Well, basically, kind of testing this out to see how it works. You can do this instead. You can say equals new animal. So now it's a pointer, and we have a little bit more control over it. Like the way to get rid of the non-pointer one is to basically have it go out of scope. But the way to get rid of this one is, well, we can call our memory management functions on it to get rid of it. So these are all going to now be pointers, pointer, dereference there. But now when we move this, we need to dereference. And that might work. Let's give it a try. Yeah, it worked. Let's try it there. Looks fine. So what we want to do here is after we finish moving it, we can delete the old cat. So we can call delete cat. That's the original one. And then we can also set it to null pointer. And that way we can't accidentally, well, it's just more obvious now that it's no longer viable data. So what happens if we try to call a function on this old cat? Well, we should get some error of some sort. Let's see what we get here. Compiler doesn't detect it. Still get a segmentation fault because it's no longer there. Now this move, now to be honest, I'm kind of getting it a little in over my head at this point and probably making this more confusing. But just know that once you move it, the old one's gone. You can't use it anymore unless you reallocate it. Because as you can see, we've done all this and we tried to get fullness again. But what you actually want to do is you want to do a null check if, and you can just do it like this, if it exists. So you're probably going to have, code bouncing around between functions, doing special stuff. It's not necessarily going to be a nice straight down the line thing like you're seeing here. So you want to do these null checks, basically. So let's do this. Do it clear, and we'll just run it. And you can see it doesn't even call the second one because this fails and skips over it. So what we can do instead, if you want, you could reallocate a new one or something like that. There are options here. So if not cat, we'll say cat equals new animal once again. And then we should be able to get the fullness again. And run it. And there's the cat, nice and reset. Okay, well, I don't want to make this any more confusing than I've probably made it to this point. So that's kind of the crux of this pointer to the implementation. There's a whole lot more you can do, but hopefully this makes sense. The main thing here is that these implementation details are fully private, and this is more of just an interface. So if you just update this implementation here, anything that is using your animal class is not necessarily going to need to recompile. So it works pretty decently for interfaces a lot of times. And just one last thing I want to show here that was mentioned in some of those documents is sometimes you want this implementation to be able to talk back to this actual public interface. So you might have, let's say for example, a function that's like boolean can eat. Let's say that. If I can spell. That looks like one word. Okay. So you want to know if it can eat or not. That's basically all this function is going to do. So let's go ahead and define it. And it is going to be defined outside this implementation because it is just part of the animal. Now this is just a naive example. Like you might even want this as part of the implementation in reality, but for the case or the sake of example, this is a bad example. Let's say something else, like maybe we don't want in the implementation whether it's dead or alive. Maybe that's like something that's a little more public. So we'll say is alive. That's pretty standard, a pretty common function to have. So is alive, and we're just going to return true all the time. For now, we'll just say it's always alive. No dead cats around here. We're not that close to Halloween. Okay, so the point here is maybe you want to check if it's alive before it eats. So instead of calling, well, instead of this, let's see, this eat command, just calling this directly, maybe it calls another function, and we have publicly an animal here called animal. Well, let's see here. We'll just say void. Okay, we'll just make the function here basically. Void eat int calories, and we'll define the function right here. And we'll essentially do the same thing, except we don't need to make this call all the time to this because we have access to that member right there. So we can get rid of all these pImpl dereferencedness. All right, let's indent that properly so it can actually be read. And well, the problem here is we're not going to have access to max fullness. Well, we can access it by going something like this. So that'll be fine. But that might be getting a little wonky. I don't know if that'll even compile. But okay, the point is now we can delete all this. And we can just call the implementation of eat and pass it those calories. However, what if we want to check if it's alive here? Check if cat is alive first. Well, that function is part of animal as well. It's not static, so we can't just get to it like so with this max fullness thing. So what we have to do is in this call here, we want to pass it a reference back to itself, back to the interface. So we will be passing it star this. And then this function up here needs to take animal. And we need a name here. I'll just call it A. And then we can check if it's alive by going A is alive. And then we do the whole thing. Put some brackets around this so it works. Tab this over. And let's see if that works. Now, of course, is alive is just always going to be true, but we just want to see that it still works as we expect. So let's run make again. And we get some errors. Calories was not, oh, I renamed this. So it's just cal. Let's give it the full name here. That'll be a little easier to work with. Clear, make. Oh, is alive is a function. So we need to call it like a function. Very good. All right, clear. We're gonna make cannot convert animal to animal star. Okay. All right, so this needs to basically, we want it to be a const animal reference, because this is going to reference the class basically. I think that's right. So let's call make again. It's a non-pointer type, it says. Okay, so let's do that. Let's try that. Passing const discards quantifier. Okay, so that's maybe where we want the const thing to be a little more. Or the propagate const. That's probably where the propagate const comes in. It looks like it doesn't know what. Oh, we're doing this in caps for some reason. We don't want to do that. Okay, so just cleaning up a few basic errors. And there we go. We get it to work. And it works correctly. And yeah, so that's how you pass your implementation the front end. So it can call any of its public functions like this is alive or whatever you may have. And there we go. But now they are coupled together both ways, and it's a little different, but it can be done, and that's how you do it. And that's all I wanted to show there. It's just basically forwarding it along with the interface like so, because that is often done if you want to check something before you continue, like whether it's shown or hidden or whether it's alive or something like that. Well, that's pretty much it for this episode. Thank you all for watching. Special shout out to my patrons for making episodes like these possible. We do have some new funding goals up. Hopefully we can meet them to keep all these videos continuing. I really appreciate you guys, and we'll see you next episode. Peace out.